This, to me, is where physics 12 really begins. Normally, this is where you're running into your first brand new, never seen before stuff, except for you folks with COVID last year, I didn't get to work in energy. So for you folks, work in energy was where physics 12 started. It was the brand new stuff. This is normally where the brand new stuff happens. And this is some of the coolest stuff. So here's my question. Is it possible for an object to have a constant speed and yet still be accelerating? Ali says yes. Ali is correct. How can you be having a constant speed and still be accelerating? What about circular motion? I mean, Connor was clever enough to look at the title and figure, that's gotta be it. Okay. By the way, I'll say you can't have a constant velocity and still be accelerating. You can't have a constant speed and still be accelerating. I don't get what this means, Carter. Okay. What's the difference between speed and velocity? Which one is a vector? And all vectors have both magnitude and what? So you can be accelerating by changing your speed or by changing your, like when you're going around a corner. Okay? So how can you be accelerating even if you're at a constant speed? Changing direction. And specifically in our example, going in a circle. So we're going to talk about uniform circular motion. Uniform circular motion is you're going around in a circle, but you're not stepping on the gas or stepping on the brakes. Your speed isn't changing, only your direction is. We can, and we'll look at a couple of situations where your speed is also changing, but really you need calculus to deal with that. So we're almost always going to be looking at uniform circular motion. Its velocity is changing, Cleo, not because its speed magnitude is changing, but because the direction is changing. But if the velocity is changing, it must be accelerating, because an acceleration is a change in velocity. And Karn, this is the most important fact to keep in mind. If you're going in a circle, you are accelerating. The net force is not zero. There is a winner and a loser when we start doing winner minus loser equals ma. Okay? Forces are not balanced, not if you're moving in a circle. So here's kind of a top view. Typically, we say that your velocity is, don't write this down, at right angles to the radius. Don't write that down. The fancy phrase is we say tangent to the radius. That's what we're going to write down. So we're going to write velocity is, quote, tangent to the radius. And tangent really means perpendicular to. Except, in pre-calc 11 last year, I know Mr. Gerard does a little calculus intro sometimes. I don't know if he got to it with spring break, after spring break being so weird, but we talk about a tangent line. A tangent line is a line, that's a terrible drawing of a tangent line, that just kisses a curve without crossing it. It hits that curve at exactly 90 degrees, tangent to the curve. And so the velocity directions are at a right angle to the radius. If you're ever moving in a circle and you want to know your direction, look at the center of the circle, draw a 90-degree angle to that. Okay. What's the direction of the acceleration? Well, we're going to do a little vector subtraction. How do I subtract vectors? I don't. I add the opposite. We're going to start out with good old VF equals VI plus AT. We're going to get the A by itself. VF minus VI over T. Time is a scalar. So the direction of the acceleration is going to be the direction of VF minus VI, whatever it is. That's not going to be the magnitude, but that'll be the direction. By the way, I'm going to show that our acceleration isn't constant, and so this relationship is only true for a very small time interval. It's only true for a limit as delta t approaches 0, but we're fudging things here. We can find the direction, Karn, by going VF minus VI, as long as we don't let time go very far. Let's have a split second between these two velocities. So here's our top view. Here's VI, and a split second later, there's VF. I'd like to find VF minus VI. So VF looks like this. VI looks like this. Slightly at a higher angle, yes? How do I subtract vectors? I don't. What do I do instead? So this is going to be VF plus the opposite of VI. So let's draw that. There's VF. VI is up and to the right, up and to the left. What would the opposite of VI be? Tip to tail. Here's VF. Here's VI. And the resultant is from the tail of the first to the tip of the second. If I now put this on the circle, do you know which way we're accelerating? Towards the center. If you're going in a circle, you're accelerating towards the center of the circle. This also goes back last year. I taught you your bodies are backwards accelerometers. When you speed up, you feel like you're getting pushed back. When you hit the brakes, you feel like you're getting pushed forward. Hey, when you go around a circle, which way do you feel like you're getting pushed? Outwards. So which way are you accelerating? Inwards, towards the center. Okay? An object accelerating in a circle is, underline this, accelerating towards the center. That's going to be our direction, Aiden. Who's winning? Towards the center. Who's the loser? Away from the center. Who's winning? Toward the center. Who's losing? Anything pointing away from the center. Okay? And you can do that. Here's the algebraic proof, or you can remember that I taught you last year. Your body is a backwards accelerometer, so whichever way you think like you're getting pushed, the acceleration is in the opposite direction. Example 3. Suppose we have a top view. A ball is on a frictionless tabletop, and it's being rolled along a circular track as seen below. The track is not completed. It comes to an end right there. When the ball leaves the track, which path will it trace out? Path A, because the ball has some circular momentum that keeps it moving in a circular path for a while after it leaves the track. Path B, because when there's no force from the track, the object's going to go in a straight line, steady speed. Or path C, because when the track is no longer supplying a force on the ball will fly outwards. Once again, we're going to vote. Once again, high, hold your hand up. So sure you are of the answer. Oh, come on, you've missed these. Okay. So if this ball is traveling in a circle and it comes to this section of track where it ends, which path is it going to follow? Who says path A? It's going to keep going in a circle. Path A. Path B. There was a real late peer pressure. Are you voting or you're not yet? You're still thinking? I can hear the hamster on the wheel. Squeak, 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 squeak. Path C. Connor. And he's not here today, but we all know Noah would totally vote with, we know, right? Come on, it's Noah being Noah. Shout out to Noah at home, wherever he is. Okay. Why is path B correct? As soon as it leaves here, are there any forces acting on it? So then it's going to travel in a straight line at steady speed. But what that also means is, while it's in the track, there must be an unbalanced force acting on it. And that's what we're going to start to talk about even more. Okay. The real question is, why is it, next page, why is the acceleration inwards when the push you feel when you're going around the corner in a car is outwards? And the answer is you're actually not feeling a push. You're feeling your body's own inertia wanting to keep going in a straight line at a steady speed. How many of you have driven? Okay, so when you're in the driver's seat and you're going around a corner, you're getting, it says you're making a left turn. Let's say you're making a left turn, okay? Your body wants to keep going in a straight line at a steady speed. It wants to keep going in that direction. And so you physically have to pull on the steering wheel through your arms. You're actually pulling your body in this direction to get it to go around the corner. That's when you're in the driver's seat. You don't notice it. You think you're steering into the corner and you're gripping hard, but check it next time you're driving and you'll suddenly realize, wait a minute, I'm having to apply a much bigger force through my arms on this steering wheel than I do when I'm going on a straight line. When you're in the passenger seat, do you have a steering wheel to hold on to? So when you're in the passenger seat, you get pushed against the door. No, you don't. Your body kept going in a straight line at a steady speed. The car turned underneath you. The door ran into you. It's the door that's applying a force to you. That's what's pushing you around the corner. Okay. You might check with your grandfather. He may fess up to this. In the 1950s and 60s, seatbelts were not mandatory, so nobody wore seatbelts. And most front seats of cars were bench seats, like a pickup truck, not bucket seats. And so if you were a young teenage boy going out on a date, you would get some surfer's wax and you would wax down your car seat and you would drive with your right hand on the back of the seat and you would make a quick right turn as fast as you could, and the girl would come sliding into you and you would go, there, hi honey, that's very, very nice, because she wasn't wearing a seatbelt and there was nothing for her to grab onto. Okay, ask your granddad, he might know that. Okay?
Like you know.
Okay? I'm not that old, sadly. But that's actually not what was going on. If you're making a turn in that direction, the girl was going in a straight line at a steady speed. It was the car that was moving underneath. It was actually the driver moving into the path of the girl. It's just we don't think of it that way, but that's really what's going on here. Okay? From the point of view of the driver inside the car, this straight line motion seems to be outwards toward the passenger side door. That's because you want to keep going in a straight line at a steady speed. Something has to apply a force on you to change it. Put your pencils down, look up. The reason I'm harping on this discussion is important because many years of experience in your cars makes you think that there is an outwards force. There is not. There's even a term you may have heard called centrifugal force, which refers to this apparent outwards push. There is not an outwards push. A bird's eye view confirms us that the outwards push is not outwards, it's in a straight line tangent to the radius, and it's not a push at all, it's inertia. It's Newton's first. You keep going in a straight line at a steady speed. Once that force is removed, the inwards force is removed from you. And vector analysis, as done previously, shows us that the acceleration and therefore the force are actually inwards. If you're moving in a circle, which way are you accelerating? Inwards. If there's one thing that I need you to grasp that's different from what you thought, if you're moving in a circle, you're accelerating inwards. If fighter pilots move too fast into a loop, they can become unconscious due to a lack of blood flow to the brain. In fact, you'll often hear people say, oh, the blood got forced to my feet. No, that's not what happened. What really happened? Well, there's their blood in their torso, and there's the blood in their brain. Okay? The plane applied a force on the body upwards. What path are they tracing out? Which way is the net force? Toward the? So they're accelerating in that direction, but their blood is liquid. It's not attached to anything. It wants to keep going in a straight line at a steady speed. And so really what happens, it's not, Aiden, that their blood got forced from their forced down to their feet. It's that their torso got forced away from their blood, and so the blood ends up in their legs and thighs and feet. And you can become unconscious. Okay? It's called Gloc, stands for gravity-induced loss of consciousness. Gloc is what they call it. Put your pencils down, look up. There was a pilot named Douglas Bader during the Battle of Britain. When Britain's future hung on a thread, there was a desperate shortage of pilots. Douglas Bader was a pilot and his plane crashed, and in the crash he lost both of his legs just above the knees. But there was such a shortage of pilots and he was fine everywhere else. What they did is they just took another plane and they extended the pedals and he was able to still fly. And he realized because he had no legs, he could go into a dive and then pull up and take way more G's than an average person. And so what he would do is he would let the German fighters get really close behind him. He would dive, and fighters around the world being fairly macho, and if you can do it, so can I, the German pilot would follow him. Then he would pull up, not losing consciousness. Of course, fighter pilots being macho, and if you can do it, I can do it. The German pilot would try and pull up, suffered G-lock, and crash into the ground. And it reached the point where they memorized his plane's serial number and they would radio each other. The Germans, we don't know what he's doing. He can do something we can't. Don't follow him. You're not going to be able to do that. It's a true story. So, what direction is the acceleration? Toward the? How do we calculate it? There is a lovely proof, but it's a bit long. I'm just going to give you the scalar equation. Acceleration in a circle, I use AC, is equal to v squared over r. What do you think v stands for? Speed, going to be fussy, and r is the radius. And you can even put, if you want to, a little c underneath the v. It's your centripetal or circular velocity. It's how fast you're traveling in a circle. Okay? If you're not speeding up or slowing down, that means that I can take this equation and since you're not accelerating speed-wise, you're accelerating direction-wise, I can turn it into that. Oh, and if you're going at a constant speed, is v initial the same as v final? So actually I can turn it into that. And then get the v by itself. How? Okay? Your speed when you're going around a circle is equal to the distance divided by the time. We have a fancy name for once around a circle. The perimeter of a circle. It starts with the letter C. The circumference. When you're going around a circle, the distance you travel is 2 pi r, circumference. And then now I'm going to introduce a new concept to you. Whenever you accomplish one cycle or one circle, we call that the period, capital T. That's how long it takes you to go around once. And so, if you want to know how fast you're traveling in a circle, it's 2 pi r over the period, capital T, where capital T is how long it takes to go around once. I think I put both of those on your formula sheet. You probably want your formula sheet out if you don't have it out, just so you can see where we are. I did put both of those on there, right, Josh? Okay. The yellow sheet's taking a bit of a beating there, my friend. Okay. Now, period is how long to go around once. That's the easiest one to find. If we were in a normal year and we were going to Playland, and I wish we could, what you would do when you were standing in line is you would watch somebody on the ride in front of you, if it's a ride that goes in a circle, and on your smartphone you would just time how long it takes to go around once, and now you've got the period. So, for example, the Music Express. That's the one near the pirate ship at Playland. That's the ride where the disc jockey, who wants to go faster? Faster! It goes in a circle really, really fast. You would time, you just pick somebody, start your stopwatch when they're right in front of you, and stop it when they're back. You get the period in seconds. There's a concept closely related to the period, and that is frequency. They're reciprocals of each other. If it takes 3 seconds to go around once, the frequency is 1/3. If it takes 5 seconds to go around once, the frequency is 1/5, although we decimalize it, 0.2. If it takes 10 seconds to go around once, the frequency is 0.1. Oh, If you go around 5 times in 1 second, that's your frequency, 5 times per second. How long to go around once? 1/5 of a second. Okay? So, period is measured in seconds for 1 cycle. Frequency is measured in cycles for 1 second. Its symbol is a lowercase f, but cycles per second, we have a special name for that, which you've probably heard, it's hertz. You may have heard about, for example, Wi-Fi signals being at so and so many gigahertz or megahertz. That's telling you how many waves per second. Not circles, because Wi-Fi doesn't travel in a circle, travels in waves, but use this in trig all the time as well. Okay? Symbol for hertz, capital H, lowercase z. And they are reciprocals of each other. If you know one, you know the other. If I tell you the period, then you know the frequency. It's 1 divided by the period. Or if I tell you the frequency in hertz, then you know the period. It's 1 divided by the vice versa. Okay? I will usually give you the period, but not always. Sometimes I'll give you the frequency. Take the reciprocal. Example 6. An object is moving at 4 meters per second in uniform circular motion. It accelerates at 2 meters per second squared for 3 seconds. A says, find the final speed of the object. Okay. Aiden, what phrase is underlined? Read it loud and proud, kiddo. V final is 4 meters per second. Because uniform circular motion means you're not speeding up or slowing down. That 2 is causing it to accelerate towards the center, but it's not changing the speed. And that's kind of bizarre because I have trained you too well. I have trained you, A equals 2, T equals 3. Well, there is no VI. I'll just pretend it's 0. No, VI is not 0 here. But in this case, if you know it's uniform circular motion, your speed's not changing. And that means that if I want to find the distance traveled, that's just going to be speed times time, not plus a half AT squared, because that A, Nick, is being used to accelerate me towards the center, but not to speed up or slow down. In other words, it's going to be 4 times 3. How far have we traveled? 12 meters. What was the first equation for acceleration? What squared over what? Circular acceleration? What squared over what? V squared over R? Yes? There's a second equation. This one's more complicated, but it's much more useful if you're out in the field getting data, like at Playland. It's the one you would have used the most if we did go to Playland. It says this, look. If A equals V squared over R, and V is 2 pi R over the period, then this is really 2 pi R over the period squared over R. McKenna, is that still V squared over R? Okay. Here's V. Here's V. I squared it over R. That's V squared over R, the first acceleration equation. But we can tidy it up. McKenna, what's 2 squared? What's pi squared? I'm just going to write pi squared. What's R squared? I'm just going to write R squared. And there's a T squared divide, there is a T squared, and there's an extra R kicking around on the bottom. Oh, is there an R squared on the top? Is there an R on the bottom? One of the R's cancels. Here is your second equation for acceleration. 4 pi squared r over t squared. Which one do I use when? Carter, if I know the speed, I use v squared over r. If I know how long it took to go around once, the period, or the frequency, which is the reciprocal of that, I'll use this one. This is the one, because when you're out at Playland, it's much easier to time something going around once than to try and figure out how fast it went whizzing past you. There are apps for that, but they're never very accurate. This is the one that you would use the most at Playland. Okay. Same equation, just different forms. So let's summarize. AC equals v squared over r, or AC equals 4 pi squared r over t squared. Oh, and F equals what? So FC in a circle equals MAC. So now if you're moving in a circle, it's going to be winner minus loser equals MAC. Which A? It depends. If they gave you the speed, use that one. If they gave you the period, use that one. Where T is the period, how long to go around once in seconds. R is the radius, and V is the circular speed, and if you need to calculate it, it's distance over time, which is 2 pi r, circumference, over the period, distance over time. So it's kind of weird, Will. In uniform circular motion, remember Aiden not speeding up or slowing down, we have a strange situation. We're at constant speed and accelerating. What's the acceleration changing? Not the speed, but the... Looking for a word that starts with the letter D. Direction. Direction. Okay? So the acceleration is due to a changing direction, not a changing speed. And the acceleration vector is always changing direction, because if you're right here, that's which way your acceleration is pointing. If you're right here, that's which way your acceleration is pointing. If you're right here, acceleration is pointing straight up. If you're at the top, acceleration is pointing straight down. So we have a situation where I'm not going to ask you the direction in terms of north, south, east, and west. Which way you're accelerating? Towards the middle, center. And that will take care of anywhere on the circle. Okay? What this also means is we can't use our constant acceleration equations because the acceleration is changing. Not its magnitude, but its direction is. So I can't use Vf equals Vi plus At, or D equals Vit plus a half At squared, or Vf squared equals Vit plus 2Ad. Instead, I have to use my uniform kinematics equations, uniform circular kinematics equations. AC is V squared over R, or 4 pi squared R over T squared. And V is 2 pi R over T. And if you want me to find the distance, it's going to be Vt, not plus a half At squared, even though there is an A. Not speeding up or slowing down. It's pulling me in a circle. Having said that, don't write this down, but you'll almost never use those. I'm just letting you know that we can't use our kinematics stuff. Got to use circular motion stuff. Ooh, here's a nice thought experiment. The Earth is currently rotating. Oh, I can't believe I have to. Sorry. Pause the video for a second. So, let's go superhero movie. Let's imagine through some cosmic catastrophe, the Earth instantly stopped spinning. But those of us that were on the Earth maintained our centripetal velocity. We would all go flying into a wall due to our inertia. First question, which wall would we go flying into? North, south, west, or east? There are two you should be able to get rid of. Two directions you should be able to get rid of. Okay, so it ain't north and south. Now, let's see if we can puzzle this out. I yelled at you that the Earth is round. Where does the sun rise? What direction? East or west? Okay, east. But it doesn't rise, right? It stays where it is. East is that way. The sun isn't what's moving. What's moving? So for the sun to appear to us to start doing that means the Earth is moving which way? East or west? Earth is spinning that way. Okay? So we would all go flying into the east wall. That wall. So sorry, Connor and Will and Allie and Ariana, we'd all be piling on top of you. You would hit first. We'd be piling on top of you. That's a good question. How fast would people at the equator go flying into the wall? What does this question want me to find? What path are the people on the equator tracing out? Okay, so it wants me to find a centripetal speed, a circular speed. What was our new equation for circular speed from your formula sheet, please? Not for acceleration, for speed. 2 pi r over the period. So it's going to be 2 pi. I don't suppose I gave you the radius of the Earth on your formula sheet, which by now all of you should have out. So we're going to start to use, you now have on your formula sheet, there's a big table of data. And I did give you, among other things, the radius of the Earth, which is what? 6.38 times 10 to the 6th meters. All over. What's the period of the Earth? Sorry? Yeah. Well, no, I'm doing this at the equator. So I thought of that. Look, it says, how fast do people at the equator go flying into the wall? Patience, grasshopper. What's the period? How long does it take the Earth to rotate around once? 56 minutes? How many hours does it take the Earth to go around once?
You were talking to me about that the other day.
How many hours does it take the Earth to go around once?
4 hours.
Okay, so how do I convert that to seconds? So times 60 times 60, what do you get? $86,400. And that's what it says on your formula sheet too, right? It says that the period of the Earth is 86400. Right where the radius of the Earth is? Does it say that the period of the Earth is 86,400 seconds? It says that the period of the Earth is 86,400 seconds?
No, it doesn't. It says it's 86,001.
What? Duick, are you telling me that one day is not
See, I was right.
24 hours? Or did they make a mistake on the formula sheet? So, Karn, it depends what you mean by a day. Okay? There's several different ways to talk about what you mean by one day. If we put the Earth in the middle of the universe away from anything, and we asked, how long does it take to spin around once? The answer is 86,100 seconds, like on your formula sheet. If we ask, because we don't measure, that's called the stellar day. That's the length of one day, how long it takes the same part of the Earth to point to the same star again. Okay? We don't measure days like that. What are we concerned with when the sun comes up? That takes 24 hours, but the reason it takes a little bit longer than a day is because the Earth has to rotate a tiny bit further than 360 degrees for the sun to come up. Why is that? Good question. Pause the video. So I'm going to put 86,100 since it's on my formula sheet. How fast will we all go crashing into the east wall? Because this is what we wanted to find out. Try it. This is also my way of saying, hey, you're going to need to be using some scientific notation during this unit, so make sure you know how to do that. You're also going to need to find your pi button. And you should get 465.5833. If you don't know how to find your scientific notation or your pi buttons, now is your chance to ask. Pause the video for a second. 465.6 meters per... How many kilometers per hour is that? So we're splatting. Like it would be a blender over there. It would be gooey yuckiness. Okay? Where on Earth would your preferred location be if such a disaster were to actually occur? We don't have any settlements on the North Pole, but we do have permanent settlements year-round at the South Pole. They would not notice anything until their radio calls stopped getting returned. Then they would start to go, So if you want more information, there's a great website. XKCD is a ex-physicist engineer who does techie nerd comics, but he also runs a webpage called What If, where people write in with ridiculous questions, and he dives into the physics of, okay, is it possible? For example, could you drop a steak from orbit, a beef steak, and have it arrive on the Earth exactly medium rare based on the heat from friction? Okay? He also, someone said, what if the Earth instantly stopped rotating? And he will dive into wind speeds and shear speeds and the whole schmear. So if you asked, what if you were at an altitude? I'm pretty sure he talked about that. So if you want to dive down a wonderful rabbit hole of questions you never thought you to ask, but now that the question is asked, I kind of want to know. He will dive heavily into the physics of all of them, okay? Mr. Dewick is now going to go off on a little bit of a tangent. He's going to talk a bit about angular momentum and show you some cool demonstrations, as well as some addictive toys through which you can get some bonus marks on tests. First of all, what's your homework? Number 1. Okay, you have all the information you need on your formula sheet. So frequency would be 1 over the period, so 1 divided by 86,100. Speed, 2 pi r over the period. We just calculated that actually. But inwards acceleration, we didn't calculate. You can do that. Same for the moon. Okay. Same for the Earth around the sun. That information is all on your formula sheet. 4 is good. Explain how the spin cycle in a washing machine works to partially dry clothing. Okay. 5 is good. Skip 6. 7 is good. 8 is good. 9 is good. And we'll pause there.